upon upgrades and the future experiment. So this was done with, is it working? No. Yeah, now it should be working, yeah. So this was done with Schenk, so we are both conveners of this working group. So what I will discuss is basically different aspects that we had during the meetings. So we discussed the search for actions, dark photons, Z exchanges, looking for invisible objects at the LHC, and then we had also some discussion about future accelerators. So, yeah, no, it's again the same problem. So I don't know what to do with this. I mean, it's very strange that we have double slide like this. Anyway, so it's a small slide in that case, but it's the same problem as before. So I just want to remind you just a reminder for this, what we studied in the past, because this was the starting point of the future studies that I will show you. So basically, the idea is to look at proton-proton interaction, like in this case, via photon exchange. And you can produce, as an example, W pair, photon pair, or 2Z, so with the intact proton in the final state. So why is it interesting? It's because we are detecting all the particles in the final state with this kind of events. So basically, we can control the background by, for instance, matching the mass of the two protons with the mass of the W pair or the mass of the two photons, which is here. W, of course, is more tricky because we have the neutrinos in the case of leptonic decays. But in the case of the two photons, which is illustrated on this plot, this is the ratio of the mass of the two protons and the mass of the two photons, you see that our signal peaks around 1, whereas basically the background, which is dominated by two photons, plus the two protons coming from the pileup events, you get almost a flat distribution. And this is the same for the difference in rapidity between the two photon system and the two proton system. Again, for the signal, we have two photons and two protons and nothing else, so the difference in rapidity is close to 0, whereas you get a flat distribution for the two photon plus pileup events. So this is a nice way to get rid of the background. And basically, I just wanted to illustrate this, I mean, on this plot, which is here. So you expect for 300 inverse femtobard at the LHC of the order of 0.2 events of background. So negligible background, even for 300 inverse femtobard at the LHC. So I just wanted to recall this, because basically, just to mention again that this is a starting point that I will discuss now. So I just wanted to show you again briefly the reach. So the reach that we have concerning the 4-photon anomalous coupling at the LHC is of the order of a few 10 to minus 14, or even if you go to 95% confidence level limits, you go to a few 10 to minus 15. So typically, the order of magnitude, you reach about 10 to minus 14 on the 4-photon anomalous coupling. And if we want to compare this kind of reach with respect to the standard reach at the LHC, without detecting the protons, we gain about 2 orders of magnitude on the reach of the coupling, again with 300 inverse femtobard. So this is the case for gamma-gamma, so 4-photon anomalous coupling, also gamma-gamma WW and gamma-gamma ZZ. And if you look for 3 photons, so gamma-gamma-gamma Z coupling, you even gain 3 orders of magnitude. So we gain even more for this kind of 3 photon and 1 Z anomalous coupling. So just to show you the value. So what we discuss, and Diogo is interested in this kind of studies because of this model, so we'll go on the discussion related to this, is basically the main question. So we consider this photon exchange, and what about Z boson exchange? You can replace here the photon by a Z boson, and you can produce either 2W or 2Z in this way, or in addition gamma Z, so you have the 1 photon and 1 Z exchange. So for this exchange, we will have to replace the equivalent photon approximation by an equivalent Z approximation that we need to put in the code. And if we want to have an expectation for the cross-section, of course it will be very small, because it's very difficult for the proton to emit a Z boson without being destroyed. So the first cross-section estimate, I mean just by hand, will be simply the ratio of the mass of the Z boson divided by the mass of the proton to the 4th power, which gives you a factor 10 to the 8th. I mean, reduction of the cross-section. So it's a huge factor. But in fact, it depends very much on what will be the coupling ZZWW or 4Z coupling, anomalous coupling that is predicted by the model. So this will be basically the next step. So we want to put this inside the Monte Carlo, see what we get, and this will be depending on the model, which will be the 4Z coupling or 2Z and the 2W coupling that we want to put in. And so this, we don't have any result now, but the idea is to pursue this study, and especially with Diogo, and see what it gives, basically. Okay, so then the other step that I wanted to do is to look also in the same way we can look for actions. So it's again photon-photon going to actions, and what we consider is decaying into photons. So this is the present situation that we have now. So you have here the 1 over the coupling as a function of the mass of the action. So it's in logarithmic scale. So you see that basically the LHC is standing here. So we have CDF, which is here, and this is the LHC experiment. And this is the lead-lead experiment, the part of the LHC, which is here. So of course, I mean, we don't intend to be that sensitive to low mass at the LHC, but what we wanted to see in the same way that we have this kind of events where you produce 2 photons in the final state and 2 intact protons, can we say something about the search for actions? So this was the basic question that we raised during the meeting. And indeed, so this is a plot that Christian, one of my graduate students, who is in Kansas, did over the previous day, basically, which is the kind of sensitivity plot. So again, 1 of the coupling as a function of the mass of the axion. And this is the reach that you get. So if you compare, so this is basically 1 TeV, which is here. And we see that we extend our sensitivity beyond 1 TeV. Here, this is 10 TeV. Whereas you see this plot, which is a sensitivity, stops basically at 1 TeV. So using the same kind of way that we were doing this 4-photon anomalous coupling, we get sensitivity into a region where the LHC was not sensitive until now, basically, which is for high mass axion production. So all this domain is completely new. So this is what was done by Christian and Gero and Sylvain, was to consider a spin zero even resonance. For now, we use the constant width, so this will be modified in the updated version, but we wanted to get at least 1 plot to show you today. That's why we did it quickly with a constant width. So what I wanted to stress also, if we go back to this plot, is so we extend, you see the sensitivity domain of the LHC, which is here, to higher mass. And it's also complementarity with the lead-lead running. Because what is going on in lead-lead, instead of proton-proton, if you want to have the same diagram, but instead of the proton, you have lead-lead. So you enhance the cross-section by a factor which is z to the 4. So basically, the cross-section is very much enhanced in the case of lead-lead. And then you can measure this diphoton production at low mass. Because for lead-lead collision, you get a much higher cross-section and you are sensitive to the standard model part. And unfortunately, it's not sensitive to anomalous coupling or to high mass events for 2 reasons. First of all, the lead is a quite big object. So we have a cut on the impact parameter between the 2 lead events in order to get basically an ultra-peripheral collision, which we need in case of photon exchange. So this cut completely suppresses the high mass part of the cross-section. And also because the luminosity is very low, as you know, in lead-lead collisions. But still, this kind of events get sensitivity on the axion part, axion search, for the mass around 1 GeV, let's say a few GeV. So this is the exclusion plot, which is here. So basically, we have 3 different complementary search of fraction at the LHC that cover different domains. The lead-lead part, which is the lower mass. Then the standard LHC part, which is basically looking at the Z events decaying into 3 photons, mainly. And what we put a new part, which is basically looking at 2 photon productions with 2 intact protons, which cover basically this region, which is not covered at all at very high mass. And I should mention that the study is also being performed now for the FCC, so for Future Accelerator by Patricia. Okay, so just as a game, so Sylvain made a game yesterday just to put what would be the sensitivity on the previous plot. So this is the black line, which is here. And you see that basically, indeed, we cover this region, which has never been covered by the LHC. So we gain a bit, as expected, in the mass, which is a few hundred GeV, and especially all the mass above 1 TeV, which was not covered at all by the LHC, can be covered by measuring the 2 photons. So then we discussed also with Sheng on another topic, which will be developed also in the next future, so which is the search for the dark photon, which is here. So again, the same idea, photon-photon interactions, 2 intact protons in the final state. And then there are, in this blob, we can produce some dark photons, which are here gamma prime, through an exchange of action. So this is basically what we assume for this kind of model. And this dark photon decay into standard model particles, which are here. So these are the signature that we would like to look at. So also, of course, the dark photon decay dominantly into dark particles, which will not be visible unless the dark particle decay back to standard model particles. And I will mention actually that we can look also for a dark or invisible object at the LHC using other methods at the end of this talk. And what would be the observable? So what we are going to try in the near future is to look at the 4 lepton final state. Because if we assume the dark photon to decay into E plus, E minus, or mu plus, mu minus, the signature would be 2 intact protons plus either 4 electrons, 2 electrons to muon, or 4 muons, and again the 2 intact protons to suppress, to basically cancel the background. So we are going to see, for now we cannot give you some plots, but at least the aim is to, in the near future, to see how sensitive we are for the dark photon using the same kind of techniques as the LHC. And we will implement the matrix element inside our Monte Carlo, which is called FPMC for Forward Physics Monte Carlo. We are going to implement this inside the Monte Carlo. Yes? Yes, yes. I mean, the question would be more for Sheng than to me, actually. Who's more specialist? For lepton, the photon to ZZ, or ZZ events, so this would be, I think we have to check, but probably the background would be small, I guess, except that there is some anomalous production. Because I mean the cross-section gamma-gamma to ZZ must be small.
By exchange of the axion. The axion also comes to ZZ.
Ah, okay, I see what you mean. Yeah, yeah.
Because it cannot just couple to
yeah, to the dark photons. Let's say.
I mean, just by it comes to gamma-gamma by two invariants comes to ZZ.
Yeah.
Then you have ZZ decay into.
So maybe Cheng could comment, or maybe I can give you the microphone. Everybody to hear. That's more a question to Cheng than for me.
Yeah, I haven't thought about the coupling to Z, but I guess it also depends on the mass of Z compared to the mass of dark photons. I mean, dark photons in this case probably we consider it to be heavier, so it's more sensitive, but. Yeah, essentially it can be anything. Although initially I would like it to be about GeV, but I think according to Royon, we need it to be a lot heavier. Yeah, so. Well, essentially for like in the twin Higgs or mirror universe model, you want to avoid having a dark radiation, so you want to have a heavier photons which. Well, basically you have to break the corresponding dark electromagnetism, yeah, in U1 in the dark sector. Yeah. But to give such a, I don't know, such a heavier mass, maybe in the model building point of view is, but at least from this search perspective, it can be free parameters, yeah. Yeah, there are many complementary bounds for just dark photon searches. Yeah. Yeah. Oh, basically, it also couples to. Yeah. Yeah, the difference between dark photon and Z prime probably is not very different in this case, yeah.
Typically, the word dark photon came from no gauge coupling whatsoever. The only thing is that it has a kinetic mixing with the photon. So once you have kinetic mixing with the photon, whatever photons or electromagnetic photons couple to anything, it will couple to everything. So it certainly depends on the mixing parameters. Only two parameters. One is the dark photon mass, and the other one is the mixing parameter epsilon. how that mixing with that. And everything is very predictable. So then I don't see why this channel is the leading contribution. And the dark photon search has been ongoing for a long, long, long time. So for the light mass, the most notable one will be upsilon decay, and the J side decay, and the lab 1, lab 2, everywhere. So it's about a lot of this. You have a charged leptons. Why you go with the intact proton? You're giving yourself a hard time, as I said. You have 2 charged leptons. It's most fantastic signature to search for at LHC. 4 leptons, no backgrounds. No background. Well, I think you're giving yourself a hard time to search for the rather rare decay channel. Very, very rare.
Yeah, okay, so maybe let's move on. So, what is this? Skip this version or remind me later? Something like that. Remind me later, yeah. Okay, good. so yeah, so let's move to the next part. Okay. So I just wanted to discuss very briefly, because I discussed it also, it was the talk which I presented last Monday, the way to discuss also some invisible mass object in Atlas and the CMS. So this could be some dark matter particle, some dark matter particle or some, for instance, magnetic monopoles, whatever can be invisible object. So the idea would be, again, if we have the same idea via photon exchange, is to detect the 2 protons. And this object cannot be detected in CMS or Atlas because they escape without detection. So this is the difficult part. So the signature is nothing in Atlas and CMS, 2 protons of high mass in CT PPS or AFP, it means the forward detectors which are in Atlas and CMS. So the idea is to request high mass object in Raman pods, found the vertex where these protons are coming from using the fast timing detector, because fast timing detector measure the time of flight of the protons, and request nothing else in CMS and Atlas pointing to that vertex. So this would be general idea. And what we need to do is to have some more detailed simulation. And the leading background will be, in fact, when there are some photon or some colorless objects which are exchanged, where there is very forward pions that are emitted. And these forward pions may escape through the beam pipe. And this cross-section is basically unknown, because we cannot trust a generator that has never been measured. So this will be the leading background, plus, in addition, the pileup events, where you see nothing inside the CMS, and the proton, there can be single diffractive proton, which have nothing to do with monopole prediction. So that's why, for control this background, what we need to measure the time of flight of all the particles which are produced in the very forward region or in the central part of the detector, especially, for instance, in the 0-degree calorimeter. And this means that we know from which vertex these particles are originating. So this is the basic idea of this kind of measurement, if we want to get it possible experimentally, is to measure the time of flight of all the particles that are produced. And in fact, so this is what is foreseen in Atlas and CMS, is to install these timing detectors everywhere now, so for basically the high luminosity LHC. And we need to request that there is incompatibility between the 2 proton vertex, which is found using the time detectors, and the vertices found using the particle in the very forward region. Okay, so I want just to mention that we had also quite some discussion during one of the meetings about the future machine, and especially the higher energy LHC, which is possible to get after the high lumi LHC. And the strategy is to develop the 16 Tesla magnet that would be needed both for the high energy LHC and the FCC. But then the question, I mean, so if we want to get the high energy LHC, which would be 2833 TeV, would not run before 2035 and should stand within the CERN budget. And clearly, in that case, I mean, why not having directly the FCC or the Chinese project, which could be also ready around this time, because these 16 Tesla magnets will be ready to be used. Or if we want to have a higher energy LHC, basically it could be at lower energy and using, for instance, the 14 Tesla magnet. There might be some compromise, so that if there is nothing really new appearing at the LHC by the beginning of high lumi LHC or the end of the next phase LHC, it's clear that there will not be 5 sigma discovery with the high luminosity LHC. So why not trying to move to a higher energy machine before accumulating 12 years of high luminosity LHC. So of course, it's not up to us to decide, but we had basically some discussion about this kind of possibility. So at the conclusion, I would say that we discussed many topics at this workshop. So the advantage of proton tagging using these photon exchange processes, because there is no background. The axion search is as presented, search for dark photon, invisible objects, and also the search for the 4Z or 2Z and 2W anomalous coupling. We had also a discussion of the future machine. And I would say an important point of this workshop that I mentioned, I mean, we didn't have time, obviously, in 2 weeks to cover everything for the dark photon, this anomalous coupling, and so on. So it's also a way to start new collaboration between people, new interactions between the also experimentalists and the theorists, which is a good aspect of this workshop. So to finish, I would like to thank all the people who took part in the working group and the organizers, so especially Benjamin, Sabine, Eduardo, and Sylvain, for this very nice workshop. And as you can see, the Jayhawk is very happy. So thank you.
I've prepared a few slides just to conclude the workshop. So that's a farewell session. I like this photo. Yeah. I think Diogo is showing off a little bit here. It's more tan than the others. So yeah, so the goal of the workshop was to discuss and work on topics related to searches for new physics. So, well, we discussed a lot. There were many interesting discussions along these 2 weeks. Okay, I took some photos with my cell phone, but okay, it's not so great. The discussion part is, well, has been successful for sure. The work part, I think it's also quite successful. Many people were working, like for example, here there is a line of people super concentrated. The wiki has been fairly filled with interesting projects. Any comments about Gero thinking about what he's going to eat at the coffee break, maybe? Yeah, so the work part is also well, quite a success, I would say. So, well, on behalf of all the organizers, I think we can say congratulations to everyone. So we can congratulate ourselves. And I would like to especially thank the conveners who have made a